Everyone, did you know that the most distant human-made object is still talking to Earth? Voyager 1 is so far away that a one-way radio message now takes more than 23 hours. By the time engineers learn whether a command worked, yesterday has already packed its bags and left. Yet, this spacecraft was built in the 1970s, has less computing power than a modern pocket calculator, and is still doing science in interstellar space. So how did two machines designed for a 5-year mission survive for almost half a century? And what did they discover that changed our picture of the solar system forever? Today, we are following Voyager from a launch pad in Florida to the space between the stars. The story begins in 1977, when disco was booming, personal computers were exotic, and nobody had yet sent a spacecraft past Saturn. Voyager 2 launched first, on August 20th. Voyager 1 followed on September 5th, but took a faster route and reached Jupiter and Saturn before its older-named twin. Yes, Voyager 2 left first and arrived second. NASA naming had already discovered time travel, at least in the filing cabinet. Each probe rode a Titan Centaur rocket and carried cameras, particle detectors, magnetometers, radio instruments, and a large dish antenna. Their official primary goal was straightforward: examine Jupiter and Saturn up close. The rest of the journey would depend on whether the spacecraft, the trajectories, and a great deal of human nerve all held together. The opportunity came from a rare arrangement of the outer planets that occurs only about once every 175 years. Jupiter, Saturn, Uranus, and Neptune were positioned so a spacecraft could use one planet's gravity to bend its path toward the next. This is called a gravity assist. The planet does not hand over fuel like a cosmic gas station. Instead, the spacecraft exchanges a tiny amount of momentum with the moving planet, stealing an almost immeasurably small fraction of its orbital energy. The planet never notices. The spacecraft very much does. Without these assists, a 4-planet tour could have taken decades longer or required far more fuel. Mission designers turned celestial mechanics into the solar system's most ambitious game of pinball, with no spare ball. The two Voyagers were nearly identical, each weighing about 825 kilograms at launch. A dish antenna about 3.7 meters across kept Earth in the center of attention. 3 radioisotope thermoelectric generators converted heat from decaying plutonium into electricity because sunlight was far too weak in the outer solar system for practical solar panels of that era. 6 onboard computers shared only about 68 kilobytes of memory and processed roughly 8,000 instructions per second. A modern smartphone can perform billions. But Voyager's computers were not asked to stream video, recommend lunch, or argue with you about software updates. They had a smaller job: point the antenna, run instruments, protect the spacecraft, and obey carefully prepared commands. They did that job with astonishing reliability. Voyager 1 reached Jupiter in March 1979, with Voyager 2 following in July. Their cameras revealed a planet that behaved less like a quiet striped ball and more like a gigantic weather laboratory. The Great Red Spot showed complex circulation, while smaller storms spun through the cloud bands. The spacecraft also studied Jupiter's immense magnetic environment, where charged particles create radiation levels dangerous to electronics. Engineers had prepared for punishment, but the data still carried surprises. Jupiter's faint ring system came into view, and its moons stopped being little points of light. They became worlds with individual geology. This was one of Voyager's greatest gifts. Objects that had lived in textbooks as names suddenly acquired cliffs, cracks, colors, weather, and in one spectacular case, active volcanoes. The most shocking discovery came from Io. In an image taken by Voyager 1, scientist Linda Morabito noticed a plume rising above the moon's edge. It was an active volcanic eruption, the first ever observed beyond Earth. The Voyagers eventually saw multiple eruptions, with plumes extending hundreds of kilometers above the surface. Io is needed by gravity. Jupiter pulls strongly, while neighboring moons disturb Io's orbit, flexing its solid body and producing intense internal heat. Imagine squeezing a stress ball until it becomes a planet-sized pizza oven. Io's surface is continually repainted by sulfur-rich material, which helps explain its bizarre yellow, orange, white, and black appearance. The discovery proved that small moons could be geologically alive, not merely frozen leftovers from the solar system's construction site. Europa offered a quieter mystery. Voyager images showed a bright, icy surface crossed by long, dark lines and relatively few large impact craters. The spacecraft did not prove that an ocean existed beneath the ice. That evidence became much stronger with later missions, especially Galileo. Today, the leading interpretation is that Europa probably hides a global salty ocean below its frozen crust, perhaps containing more water than Earth's oceans combined. Voyager supplied the first detailed clues. Ganymede revealed grooved terrain, while Callisto displayed an ancient, battered face. For large moons, orbiting the same planet had developed in dramatically different ways. Apparently, even in one cosmic neighborhood, the children can have completely different personalities. Jupiter had become not just one destination, but a miniature planetary system. Voyager 1 arrived at Saturn in November 1980, and Voyager 2 followed in August 1981. The rings, beautiful from Earth, became a maze. The cameras resolved countless narrow ringlets, gaps, waves, and braided structures shaped by gravity. Small shepherd moons helped confine some ring material, while other moons created ripples and resonances. Saturn's rings were not a single polished record. They were more like an entire record shop dropped onto an orbital racetrack. The Voyagers also studied Saturn's atmosphere, magnetic field, and moons. Enceladus looked unusually bright, although its spectacular water plumes would not be discovered until Cassini decades later. Once again, Voyager did not finish every mystery. It opened a door and left later explorers a very long list of questions. For Voyager 1, Saturn's moon Titan determined the future. Titan has a thick nitrogen-rich atmosphere, and mission planners wanted a close pass. That encounter delivered valuable measurements, but gravity bent Voyager 1 sharply northward, away from the flat plane where most planets orbit. After Titan, Voyager 1 could not continue to Uranus or Neptune. It had traded the Grand Tour for one extraordinary moon and a faster path toward interstellar space. Voyager 2 took a different route past Saturn, preserving the option to continue outward. This was not an accident or a failure. It was a deliberate choice between two priceless scientific paths. Space exploration is often described as boldly going everywhere. In practice, it is usually boldly choosing which amazing place you are willing to miss. After Saturn, Voyager 2 flew alone toward Uranus for 4.5 years. NASA had originally guaranteed only the Jupiter and Saturn mission, so every additional encounter felt like borrowed time. On January 24, 1986, Voyager 2 became the first spacecraft to visit Uranus, and it remains the only one to have done so. Sunlight there was about 400 times dimmer than at Earth, forcing long camera exposures and careful planning. The planet looked deceptively calm and pale blue-green, but Voyager measured powerful winds, discovered 10 new moons and 2 new rings, and found a magnetic field tilted about 55 degrees from the planet's rotation axis and offset from its center. Uranus was already rotating on its side. Its magnetic field apparently decided that ordinary geometry was too predictable. Then there was Miranda, a small moon with a surface that seemed assembled from mismatched pieces. Voyager photographed enormous fault canyons, ridges, valleys, and strange oval regions called coronae. Some cliffs are many times deeper than Earth's Grand Canyon. Scientists still debate how this terrain formed. An older idea proposed that Miranda had been shattered and reassembled, but other explanations involving internal heating, impacts, and icy material rising and refreezing may be more likely. This is a place where certainty matters. Voyager showed us the landscape, but the exact history remains unsettled. Miranda looks like a moon designed by a committee that lost the first 3 drafts. Yet those chaotic-looking features may preserve a detailed record of tidal heating and geological change in the cold outer solar system. Voyager 2 used Uranus for one more gravity assist and reached Neptune on August 25, 1989. No spacecraft has returned since. The images revealed a dynamic blue world with clouds and an Earth-sized storm called the Great Dark Spot. Winds near the storm reached roughly 2,000 kilometers per hour in some measurements, among the fastest known in the solar system. That was deeply inconvenient for anyone who had assumed that receiving so little sunlight should make Neptune meteorologically boring. The probe discovered new moons and rings, then skimmed past Triton, Neptune's largest moon. Mission controllers aimed for that close encounter even though it bent Voyager 2 downward and ended any further planetary tour. There was no next giant planet anyway. unless Pluto wanted to file a very complicated appeal. Triton delivered the Grand Tour's final major surprise. Its surface temperature was only around 38 Kelvin, extremely close to absolute zero, yet Voyager images showed dark streaks and geyser-like plumes rising several kilometers. The leading explanation is that sunlight warmed translucent nitrogen ice, building pressure beneath the surface until gas and dark particles erupted through vents. This interpretation remains a model rather than a video recording of the process underground, but the active plumes were real. Triton also moves around Neptune in the opposite direction from the planet's rotation, suggesting it was probably captured from the outer solar system rather than formed beside Neptune. Voyager's last planetary target was not a dead ice ball. It was active, strange, and possibly a captured dwarf planet cousin wearing a moon-shaped name tag. After the planetary encounters, Voyager 1 performed one final photographic act. On February 14, 1990, from about 6 billion kilometers from the Sun, it turned its cameras back toward the inner solar system. The result was a family portrait made from 60 images. Earth occupied about 1 pixel, suspended in a ray of scattered sunlight. This became the pale blue dot. Mars was lost in scattered light, Mercury was too close to the Sun, and Pluto was too faint. So even the solar system family portrait had relatives who missed picture day. 34 minutes after photographing Earth, Voyager took its last image. The cameras were then switched off, and their control software was eventually removed to save resources for the interstellar mission. The probe would keep exploring, but it would never look back again. Both spacecraft also carry a golden record, a 12-inch gold-plated copper disc intended as a time capsule. A committee led by Carl Sagan selected 115 images, natural sounds including wind, thunder, birds, and whales, music from different cultures and eras, and greetings in 55 languages. The aluminum cover includes symbolic instructions for playing the record, locating our sun, and estimating how long the spacecraft has traveled. Nobody expects a convenient alien turntable to appear next Tuesday. The record matters because of what humans chose to say when given one small package for the cosmos. We send equations and anatomy, but also laughter, music, weather, and ordinary life. It is less a message saying, "We understand everything," and more a hopeful note saying, "This is what being here felt like." The Voyagers then began the interstellar mission. The Sun continuously releases a flow of charged particles called the solar wind. Together with the solar magnetic field, this flow inflates a vast protective bubble called the heliosphere. Its outer boundary is the heliopause, where the solar wind gives way to the interstellar environment. Crossing that boundary does not mean Voyager has completely left the solar system. The Sun's gravity extends far beyond the heliopause, and the distant Oort cloud may reach tens of thousands of astronomical units away. So Voyager is in interstellar space, but still inside the broader gravitational domain of the Sun. It sounds contradictory only because nature did not consult our filing system before building the boundaries. Space has layers, and different scientific questions use different definitions. Voyager 1 crossed the heliopause on August 25, 2012, although scientists confirmed the milestone later. One key clue came when a solar eruption eventually reached the spacecraft and caused the surrounding plasma to oscillate. The plasma wave instrument detected the vibration, allowing researchers to calculate the local electron density. The density was much higher than expected inside the heliosphere and consistent with interstellar plasma. In other words, Voyager did not see a border sign. It listened to the environment and found that the neighborhood had changed. NASA converted those plasma oscillations into audio frequencies we can hear, often described as the sound of interstellar space. It is not sound traveling through a vacuum like a movie explosion. It is instrument data representing waves and charged particles. Space remains stubbornly unwilling to provide surround sound. Voyager 2 crossed the heliopause on November 5, 2018. Its route and working plasma science instrument gave researchers a second measurement from a different direction. The spacecraft observed the solar wind drop away and recorded changes in particles, plasma, and magnetic fields. The two crossings showed that the heliosphere is not a simple, perfectly symmetrical bubble. Conditions vary with direction and with the Sun's activity. This is why keeping both Voyagers alive matters. One measurement tells you what happened along one path. Two distant probes begin to reveal shape and variation. it is still a very small sample of an enormous boundary, rather like trying to understand an entire coastline using 2 thermometers. But those are the only thermometers humanity has ever placed there. Communication depends on NASA's Deep Space Network, with antenna complexes in California, Spain, and Australia. Earth rotates, so the 3 sites hand distant spacecraft from one part of the sky to another. Voyager transmits with roughly 20 watts, comparable to a small household light. By the time the signal reaches Earth, it is unimaginably faint, and giant antennas plus sensitive receivers must pull it from the background noise. Data arrives slowly. There is no live chat, no quick reboot, and definitely no technician driving out with a new cable. A command to Voyager 1 takes more than 23 hours one way. The reply needs the same journey back. Every serious troubleshooting step can consume 2 days before the team even knows whether the patient blinked. That delay makes recent engineering rescues remarkable. In late 2023, Voyager 1 began returning unreadable data. Engineers traced the problem to a failed memory chip in the flight data subsystem and moved pieces of software into other available locations. In 2024, readable engineering and science data returned. Then, before a major deep space network antenna pause, the team revived roll thrusters that had been considered unusable since 2004. The fix required switching heaters back on and carefully controlling orientation, because firing a frozen thruster could have been dangerous. The March 2025 test worked. Somewhere, an engineer effectively repaired half-century-old hardware from more than 23 light hours away. That is less like roadside assistance and more like teaching archaeology to perform surgery by postcard. The central limit is power. Voyager's radioisotope generators produce electricity from the heat of plutonium decay, but output falls by about 4 watts per year on each spacecraft. Engineers have switched off heaters and instruments in a carefully planned order, trying to preserve at least some interstellar science. NASA's status information updated in April 2026 lists Voyager 1's magnetometer and plasma wave subsystem as operating, with its low-energy charged particle instrument turned off on April 17th to save power. Voyager 2 still had its magnetometer, plasma wave subsystem, and cosmic ray subsystem listed as operating, while several other instruments had been shut down. These details can change as the team manages energy, so the safe conclusion is not that everything still works. It is that a shrinking set of instruments continues an active extended mission. NASA engineers believe careful power management may allow at least one instrument on each spacecraft to operate into the 2030s, although unexpected failures could end either mission sooner. Every extra year is borrowed from machines never designed for this age or environment. In November 2026, Voyager 1 is expected to become the first human-made object 1 light day from Earth. The distance light travels in 24 hours. That does not make communication impossible, but it gives the phrase, "I will get back to you tomorrow," a wonderfully literal meaning. Eventually, the transmitters will fall silent. The spacecraft themselves will continue coasting, carrying no fuel-hungry engine burn, just momentum and tiny course corrections fading into history. Silence will mark the end of contact, not the end of the voyage. Voyager 1 is heading generally toward the constellation Ophiuchus. In roughly 40,000 years, it will pass within about 1.7 light-years of the star AC plus 793888. Voyager 2 will pass at a similar distance from the star Ross 248 on a comparable timescale. Those are not close encounters by planetary standards, and neither spacecraft is aimed to enter a star system. Their greater achievement is already behind and around them. They transformed 4 giant planets and dozens of moons from remote lights into individual worlds. They also became the first functioning probes outside the heliosphere. Long after their power disappears, the golden records may survive as artifacts of a species that briefly learned how to throw a message beyond its own solar wind. Not bad for hardware with less memory than a small photograph. Voyager's story is sometimes reduced to distance, but distance is only the scoreboard. The deeper story is design, patience, and surprise. Engineers built redundancy because they knew failure was possible. Scientists kept changing their questions because every planet refused to behave like the simple models. Mission controllers learned to repair software and revive hardware across a delay measured in days. And two machines built before many of their current team members were born kept returning observations from a region no other spacecraft has sampled. For me, that is the most moving part. Voyager is not heroic because metal has courage. It is heroic because human curiosity survived inside careful engineering for far longer than anyone promised. Now, before we say goodbye, let us see whether one detail from that enormous journey stayed with you. Now everyone, it is time for a quiz. Which event sent Voyager 1 permanently away from the plane of the outer planets? A. Jupiter's intense radiation changed its guidance system. B. A close flyby of Saturn's moon Titan bent its trajectory. C. A planned engine burn after the pale blue dot photograph. The answer is B. Voyager 1's close Titan flyby provided extraordinary science, but Saturn's gravity then bent the spacecraft northward out of the planetary plane. Voyager 2 kept the route that continued to Uranus and Neptune. So, if you could place one new sound or image on a message leaving the solar system, what would you choose? I think I would include the sound of rain on a quiet window. It is ordinary here, but somewhere else it might describe an entire living world. Voyager makes me feel both very small and strangely proud. We are a species on one pale dot, yet we learned to build something that could cross the sun's protective bubble and keep whispering home for almost half a century. Thank you for traveling with me all the way to interstellar space. If you enjoyed this journey, please subscribe to the channel and join us for the next world. Until next time, I will see you in another world.